can start. So in the last lecture, just before your minors, we talked about response surface method, right? And in response surface method, how do you approximate or how do you build a surrogate model? By assuming polynomial basis. And once you assume the polynomial basis, it is nothing but classical least square regression that you do to find out the unknown parameters associated with the polynomial basis or polynomial functions, right. A natural question that will come is that is polynomial basis or let us say the polynomials 1 x, x square, x cube, are these the optimal polynomials, or should we use something else which will give us better convergence from less amount of data. So, this is the basic motivation. This is the basic motivation behind polynomial chaos expansion, which we will start today. Polynomial chaos expansion will also use polynomial basis, but you will see, not today, but you will see that this basis function are not just any basis function, but a very special type of basis function that is used in polynomial chaos expansion, and we will see that. But for today, we are not going to talk much about polynomial. We are not going to talk much about polynomial chaos expansion or surrogate modeling. Rather, we will be talking primarily about functional analysis. We will be defining some vector space, some function space, certain properties of those, and that is all that we will do today, and that will form the basis for polynomial chaos expansion that we will start discussing in our next lecture. Now, even in polynomial chaos expansion, we will be talking about primarily two types of polynomial chaos expansion. One is known as the intrusive polynomial chaos expansion. The other is known as the non-intrusive polynomial chaos expansion. In non-intrusive polynomial chaos expansion, it is very much like data driven approaches, where what you will do is kind of have x y pairs and try to find out the unknown coefficients associated with the polynomials. However, in intrusive polynomial chaos expansion, you will see that we will form differential equation in terms of the unknown coefficients. So, it will be differential equation in terms of the unknown coefficients, and then solve those coupled differential equations to find out the unknown coefficients as a function of x and t. And that is known as the intrusive polynomial chaos expansion, because for forming this differential equation you will need the governing physics of the problem in hand. So, you need to know about the physics of the problem, only then can you use the intrusive polynomial chaos expansion. Non-intrusive, you do not need the physics of the problem, you have a black box solver, you have x y pairs that you can generate, and that is good enough. But none of this we are going to see today. Today we will just lay the foundation for polynomial chaos expansion by talking about certain concepts from vector algebra, certain concepts from functional analysis. Okay. Okay. So, with that background, let us start. So, the first thing we are going to talk about is square integrable function. Square integrable function in vector space, I mean that is the total thing, but primarily the thing is that we are going to talk about is square integrable function. Okay. And these things are related, but you will find it little bit haphazard, and hopefully by the end of today's lecture we will start seeing the relation. Okay. So, square integrable function in vector space. Okay, or maybe I should write functions. Okay, so now the only thing that we'll talk about reliability is the first sentence today, and then there is no reliability today. So in reliability, what do we have? One of the things that is absolutely necessary for solving a reliability analysis problem is the, even before limit state function, uncertainty. So you need input variables, and input variables x coming from some PDF f of x, right? That is absolutely necessary, because without uncertainty there is nothing probabilistic. Without, or in the absence of probability, there is no reliability. It's either 1 or 0. There is no probability, right? So consider x to be a random variable. Now, although I am writing x to be a random variable, you should imagine x to be a vector, and it is actually a collection of random variable. It's, in our notation, I think it is k dimensional, right? So it's a random variable with PDF f x x, right? So x is a random variable, or, and that random variable can be a random vector also, I mean multivariate kind of thing, and the PDF is fx x. Okay. Now for this random variable, or with this random variable, square integrable functions in vector space is a collection of functions. So each point on that vector space will be a function. So there are infinite points in a space. So there are infinite possible functions in that space, but those functions should satisfy a very important property, and that property itself is written that it should be integrable at least. I mean, it should be, the square of that function should be integrable, which means the second moment should be finite. So if I have to write it, so we define f. F is the collection of all those functions. So it is the function collection of all those functions. So it is collection of functions. Now what can this function be? Any function that you are trying to approximate, right? But it can be any function. So in our case, we will use g to write a function. We are writing limit state function by g, but this need not be a limit state function, but it's a function, right? So it's collection of gx which maps from k dimensional space to, let's say, a scalar, where integration of, or maybe I will not write in terms of integration, I mean, where expectation with respect to the PDF, so f of g square x is less than infinite. What is it saying? So it is collection of all the function g. So g can vary, and it is a collection of all those functions. Each point in this space is a function. So it is collection of all those g functions for which expectation of the square of that function is finite. That means the variance is finite, it's not infinite, right? And this, when this property is satisfied, you call it square integrable functions, because g can take different forms. So g is functions, and each of those g the square of that g is integrable. You can compute the expectation of the square of that function. So fundamentally it is saying that the variance is well defined. The variance of a function, if it is well defined, then that is called as square integrable function. Clear?
Writing the variance specifically, because this will also be the part of the variance equation here.
Because this was not defined in terms of variance. Remember I talked about initially that the second moment, some people call it variance, some people call it the second expectation, right? Now it is, what is the name? Look at it, square integrable. The square should be integrable. That is what the name is. So that is why I am writing integration of the square, because what is this quantity? This quantity is nothing but expectation g square x f x x dx. The square is integrable with respect to some probability measure. Everything that is defined in this space is with respect to some probability measure, which is basically a PDF. So that is why the name square integrable. You can think, but then that will be mean. And g of x, there is negative positive that can cancel each other out. So that is very easy. Squared one, there is no negative positive business here. And more importantly, mean alone will not give you anything random. So when you go to and try to find out things, the minimum that you need is the first two moment. Then only you can think of randomness. If you only think about the first moment, that is not really random, that is the mean. So that is why it is square integral function, but there are other functions also. This is just one. So, g of x is a given function. And gx is not the PDF. Gx is just a function. fxx is the PDF. So it is basically, you think of a big space where each point is a function. Gx is defining one such, but g can change. And it is basically, this f is denoting all those points in that will satisfy this criteria. Okay. Now square integral function, but now it is mentioned that in vector space. Why in vector space? Because this square integral function satisfies the property of the vector space. What is the property of vector space? Correct. So if there are 2 points that I take from vector space, any linear combination of those should also belong to that same space. That is the property of vector space, exactly. So in this case also that is satisfied. That is why it is called square integrable function in vector space. So in vector space there are many things, but there are square integral functions, and that is in the vector space. So that means if you take 2 square integral function and do a weighted sum of those, the output will also be a square integrable function, right. This satisfies the property of vector space. And this is a very generic definition, not the vector space, I mean the square integrable function. I mean, it's a, many things will fall in this space, right. It's a very generic kind of definition. This satisfies the property of vector space, which is, if you have, let us say, G comma H, both of which belongs to this F, and then you have mu comma lambda belonging to some real space or a scalar, then mu G plus lambda H also belongs to the same space. That is what it means to be in a vector space, right. That is what it means to be in a vector space. Clear? Now again, as I said, I mean, you will not be able to relate it. Why am I even discussing this? So right now it is quite abstract. It will remain to be abstract, and maybe in the next lecture or towards the end of today's lecture, we will get some notion of why we started discussing this out of the blue. Okay? Because, okay. So this was the first thing, which is square integrable function in vector space. The second thing is inner product. Inner product for square integrable function in vector space. Inner product for square integrable functions, or inner product for square integrable functions in vector space. So can someone define me what is inner product? Dot product is not inner product. We are in a functional space. We are talking about functions. Now think. Inner product for square integral functions. You can see in the title itself I am writing for functions. Dot product holds only for vector. So there are similarities between the two. Actually both are almost same, but not same at the same time. What? Nothing. No. Okay. So to define it, for square integrable function, for square integrable function, which is f is equal to g. I am not writing x, g is a function of x, but I am not writing that. G mapping from R of k to R, where expectation with respect to f of g square is less than infinite, we define an operator, and this operator, how do you define dot product? What is the any operator, you know, any symbol by which you can denote dot product instead of dot? A, don't say A dot B instead of that. Angle bracket, you know that, right? So that angle bracket is actually for inner product. This is actually not for dot product, but because when you do inner product on vector or in Euclidean space, it becomes dot product. Okay. So we define an operator. Anyone, any idea what this dot means? Dot means an input it will take, because operator takes an input and it gives out an input, right? So that's what it means. Okay. And this maps from basically what is it will do? It will take two functions. It will take two functions and give you a scalar. So this is the function space f. F means function because the input is a function. If it was vector, I would have written real, but because the input is function, I am using this notation. How many function will it take as input? Two dots, so two. So f cross f, and it will map it to a, right? We define an operator that will does this, but what operation will this operator perform? I mean, there can be n number of things that this can do, right? We define operator this such that g comma h, if I have to do, is equal to integration gx hx fxx dx. This is known as the inner product of square integrable function. Obviously, here you can understand that both g and h belongs to the calligraphic f, that space, the square integrable function space, right? Both g and h belongs to that function space, capital, I mean the calligraphic f, the first equation I wrote in this slide. So these are both belonging to that space. Both g and h are square integrable function, right? Clear? Now, as I was saying, I mean, this is, I mean, sometimes you call it dot product also, but actually dot product is very specific to vectors, whereas inner product can be applied to vector, scalars, not scalar, I mean vector, function, both. So dot product, you can think of it as a special case of inner product, where inner product is applied to vector. And this is the more generalized representation because it is talking about weighing that with respect to the PDF. So the inner product is not something that will remain unchanged. The definition will remain unchanged, but if I have two square integrable function in vector space, one for x with PDF fxx, the other for y with PDF fyy, then even for same h and g, you will get different output of the inner product, because this fxx will change to fyy. So if this fxx is Gaussian and if this fxx is uniform, even if g and h are same, your result will not be same, which means inner product by definition is a function of the PDF of the random input, right?
We are not talking about anything related to PDF, then this f of x will not come.
Then without talking about PDF, there is no concept of inner product. Inner product does not exist in a generalized sense if there is no PDF. That is not a generalized inner product. The generalized inner product, if to define, you need the concept of PDF. Without that, you cannot. When you are not talking about it, you are taking it to be uniform, so that becomes 1, that goes outside, so you think there is no PDF. If it becomes 1, that's a constant that will come outside, and then you will think that there is no PDF, but the PDF is actually there, right? So there is nothing without PDF. The definition itself holds only when x and fxx are defined, and fxx means PDF. So whatever I am going to talk only holds for x is a random variable, and all these are in that space. Okay. Okay, inner product, right? What are the properties of inner product? All the properties that you know of dot product are also true for inner product. So now start telling me the properties of dot product. Correct. The first one is that it should not depend on which sequence it is in, right? It should not depend on which sequence it is, and that is quite obvious from the definition, the integration. You exchange g and h, nothing will change. So one of the property of inner product is that g comma h is equal to h comma g. Anything else? One by one. What scalar? That too I have defined. That is in the definition. That is not a property now. Yeah, how? What should I write here? You're right. What should I write? Tell me. G comma no, not h, h plus k. G comma h plus k is equal to inner product of g h plus inner product of g and k. So inner product of G comma H plus K is equal to inner product of G comma H plus inner product of G comma K. Anything else? See, in the I am also writing. Anything else? Inner product, then what does it mean? But that's a different thing. I am not even defined orthogonal function. That cannot be a property. That will come later. What will happen? What can you talk? Tell me about G comma G. Greater than or equal to 0. A dot A is greater than or equal to 0, right? That is one property, obviously. Although G comma G I will define in a spot file, but anything else? There is one more property, multiplicative. Mu G comma H, where mu is a scalar, will become mu of inner product of G and H. That is the fourth. Right? These are more or less the properties of dot product, which also holds for the inner product. Okay. Why do we care about inner product? Any idea? Can you draw some inspiration from response surface method and think? You might not be able to think, but at least try. That why do we care about inner product? Inner product space. I mean, this is inner product space actually. I have not written that, but that's okay. So why do we care about inner product space or inner product in general? Okay. And that is how 20% in the correct direction. Yeah, but why should I care about orthogonality? That's a different question. Introduce? Reduce dimension, that will not happen here. Basis function is correct, but we want to represent a function in terms of basis function, that is correct. But we will also like to know about the convergence property of those, whether the series is a convergent series or not. We do care about convergence. And how will you define convergence? Using norm or some distance metric. And norm or distance metric can only be defined, or one way, not only maybe, one way of defining this norm and distance metric is through inner product. So that is why we care about this inner product space, because we like to define basis function in this space, but we will also like to know about the convergence property, and to know about the convergence property we will need to know about or how close or far they are, some distance metric, some norm. And to define this norm and distance metric, one convenient way is to use inner product. For example, a norm I already defined somewhat, there is G comma G. What is it? It is the square of norm, right? So you can understand that why do we care about. So we care about inner product space. We care about inner product space because we are interested in convergence of functions, basis functions to be more specific, and for that we want to define metric, some distance metric, and for defining distance metrics we want to define norm, right? So that is why we are interested in
Using this convergence thing
from
MCS onward, there also we use the
that's a
convergence.
again MCS convergence was in terms of what? Number of samples. Here the convergence will be in terms of what? Number of polynomials basis. These are two different types of convergence we are talking about. MCS there is no polynomial basis, so there is no series to converge. It is only about how many samples would you draw to achieve convergence. Here the question is how many polynomial, because the polynomial basis will go up to infinite. So the question is what basis would you use and until what basis and when can you truncate it, because you will ideally want some exponential convergence for it, so that you can truncate many of those and only work with a few of those basis functions. So these are two different convergences we are talking about. It is not in terms of training or MCS samples, it is in terms of number of basis, right? So in that sense, so it is a different convergence we are talking about.
So it's like what we use in the case of form also.
We did not use, because there is nothing to decide about convergence. We decided we will use only up to first order. So if we already decide I will only use linear, which is first order, then the discussion about convergence goes out of the window, because now I don't have the flexibility to increase that order.
So this is a kind of different convergence. There it was like we were using an algorithm, convergence was there like.
That was optimization convergence.
Okay.
That was not convergence in terms of number of polynomials, because the polynomial was always linear in form, always quadratic in form. So even if it does not converge, you do not have the flexibility to let us say work with fifth order polynomial. You do not have that. So that convergence was in terms of optimization loop. The MCS convergence was in terms of number of samples. Here the convergence is number of terms. Okay. So that's why it's a different type of convergence we are talking about. Okay. Any question? Okay. So we have defined, what have we defined till now? We have defined square integrable function and we have defined the inner product. The next thing we will define is norm. So the next thing is norm. Again, I am not writing it, but it is norm of square integrable functions. So although I am writing norm, you should keep in mind that norm is basically norm of square integral function. Okay. So before I write mathematically, and you know mathematically what I am going to write, can you tell me what a norm of the function physically will mean? Physically, what a norm of a function will mean? A norm of a vector, what does it mean? Length. Because it's a vector, so you are talking about length. For a function, that length will become magnitude. How big that function is, how small that function is, intuitively you can think of that. So norm defines how big a function is or how small a function is. So it defines the magnitude of a function, right? Which in case of vector space is obviously length. Not vector space, in case of vector is its length. So this basically defines magnitude of a function. right? How will you define it? Inner product square root. So you define it as same notation, you know the norm notation of G, let's say. This is equal to inner product of G comma G to the power half, which is equal to integration Gx G square x fxx dx to the power half. This is how do you define the norm, right? Clear? And you can easily see that if it was a vector, then that norm will be, the inner product will become dot product, and you know that a dot a, if you take a square root of that, you will get the magnitude or the norm of a vector, right? Same thing, but now in a generalized sense, and in each of these definition you will see that repeatedly one thing that is coming again and again is the PDF of x. All of these are function of PDF of x, and again if the PDF is uniform versus Gaussian, your norm will change. The norm is a function of the PDF, keep that in mind, right? Okay. Okay. What are the properties of norm? It is greater than or equal to 0. That is the first thing. And the second thing is that if the norm is equal to 0, then the function is equal to 0. It does not exist. And then the third is that norm of mu of G is equal to mod of mu multiplied by norm of G. Mod because it cannot be negative. So that is why. So properties of norm. Properties of norm. So the first thing is that norm of a function G is always greater than or equal to 0. Norm of a function G equal to 0 implies that function itself is equal to 0, right? Because square of a terms, it cannot happen, right? Third one is norm of mu G is equal to mod of mu multiplied by norm of G, right? Mod is coming because non-negativity, and these are properties of norm that you are already aware of in the vector space or for a vector. Same thing holds for a function. The only thing that changes is the definition of norm, because now it's a function of PDF, right? Fine, good. These are the properties of the norm. Now what we are interested in? We are interested in talking about convergence. For talking about convergence, what do we need? Metric, distance metric, right? And then using the distance metric, we can talk about convergence. So now next thing generally therefore is distance metric. From the name itself, you know that it measures what? Distance between two functions in the space f, calligraphic f. So if you take two functions from that square integrable function space, this should measure the difference between those two functions, the distance between those two functions, right? And this you define as d. D is the distance metric between h and g, where h and g are square integrable functions, right? Then it will be equal to what? Norm of h minus g, difference between the function and norm of that. that is a distance metric. What is the difference between two vectors? You take the difference between two vectors and take the norm of that. That is what you do, right. Same thing you can do here. Whatever you do in case of vector will do for functions now. So, this will become norm of h minus g, which is equal to integration h x minus g x square f x x dx to the power half, right. And you can understand that this is giving some distance between the two, weighted by the probability measure, which is the PDF, right. What are the properties of distance metric? Always positive. So, the first property is properties of distance metric. You also call it distance metric space, by the way. Okay, all of this norm space, distance metric space, all of this I can always add a space to that. Inner product space for square integrable function. This one is distance metric space for square integrable function. And then in between there was norm space for square integrable. So, all of this is space, by the way, we are talking about. Keep that in mind. Okay. Properties. You said always less than equal to, greater than equal to 0. That is one property. Any other property of a distance metric? Distance between h and g should be equal to distance between its symmetric. H and g is equal to distance between g and h. And that is why if you have heard of KL divergence, that is not a distance metric, that is a divergence metric. So, divergence and distance are two different things. So, KL divergence is something we use often in machine learning. We will use, no, we will not use here, but we can use in Gaussian process, but we will not use. But that is known as a divergence because it is not symmetric. It is not a distance metric. Whereas norm, I mean this is a distance because this is symmetric. So, keep that in mind that often in absence of distance metrics we use divergence to know the closeness about two things, but distance metric is the ideal thing that you will like to use.
So what it is actually divergence? Is it the similar divergence what we studied
In what?
Yeah.
Yeah. No, that's the divergence operator. Yeah. This is a probabilistic divergence, Kullback-Leibler divergence. So, it gives you distance between, not distance exactly, some pseudo distance between two distributions. Now, these two are not symmetric. So, distance between P and Q or divergence between P and Q is not equal to divergence between Q and P. But it is not the divergence operator that you are thinking about in vector calculus, no, not that one. Anyways, that is not part, that is not relevant now. I just mentioned it because some of you have studied, I mean, machine learning earlier, and there this scale divergence is very common. So, that is why I am mentioning it. Okay. Specifically in generative modeling and all those things, the scale divergence is very common. Okay. There is one more thing. If d of h comma g is equal to 0, then what happens? What does it implies? H equal to g. That means they are the same, essentially the same functions, right. So, this is known as the distance metric space or metric space. Okay. So, we have defined, what have we defined till now? Square integrable function in vector space, then inner product space, norm space, and distance metric space. These are the four things we have defined. Now, we are going to define one more thing that is known as Cauchy sequences. Cauchy's sequences. Okay. Sequences. What is Cauchy's sequences? Let me first define it. I'll not write it mathematically, you can check it out, but I will define it. So Cauchy's sequences is obviously a sequence of function f1, f2, f3, f4 from a square integrable function f such that the distance between two consecutive member of the sequence keep on reducing as you go away. What does it mean? Suppose I have f1, f2, f3, f4, fn, fn minus 1. The distance between f1 and f2 and distance between fn and fn minus 1 or fn and fn plus 1, whatever you take it. The second distance fn and n plus 1 will be much smaller than the distance between first two. So as you start from 1 and as you proceed with the sequence, the distance between the two consecutive member or in this case function of the sequence keeps on reducing. If this property you observe, that is known as Cauchy's sequence. Any idea why this is important? Convergence. Because ultimately what will happen? It will collapse to a point. If you keep on increasing, after a point you can imagine it will be a single point, right? That does not happen in Cauchy's sequence. It will seem like it will happen, but it is not guaranteed it will happen. There are only certain spaces where this property holds, and that will come later. So Cauchy's sequence, the only definition is it will keep on reducing. So it will almost seem like it is converging. So it will seem to you that it is converging, but it is not guaranteed that it will converge. Why? Because it can always keep on reducing and it may never converge. And there are certain spaces where it does not converge. So having a Cauchy's sequence does not guarantee convergence, but from a practical point of view, that is all we can work with. If that is not convergent, we don't have any metric to know what is convergent. So we like to work in a space where Cauchy's sequence means convergence. We will not like to work in a space where Cauchy's sequence means or cannot guarantee convergence, because then we do not know how to determine convergence. So Cauchy's sequence is, I have f1, f2 and it goes on like this from some space f, then if it's a Cauchy sequence, then it looks like, and looks like is an important term here, a convergent series. Okay. So in reality the distance will keep on reducing, there is no doubt about that, but it need not be a convergent series. As long as the distance keeps on reducing, it is a Cauchy sequence. Okay. Now, where did you start from? Square integral function, then inner product, then non, then distance metric, right? And then we talked about Cauchy sequence. Now we will go back. Now now we will talk about complete metric set. So in the metric space, distance metric space that we define, if you find something like a Cauchy sequence, it will converge. In the metric space, this Cauchy sequence, if something looks like converging, it does converge. And if that property holds, then that is known as a complete metric set or complete metric space, set space. I'll repeat once more. What is the metric space? The distance, right? Where the distance is defined, d of h comma g. Now, even that space, if you find a sequence of function f1, f2, f3, which seems like converging, then it does converge. And if it does converge, then that is known as a complete metric space. Okay. So here, if it seems like converging, it does converge, right? If it seems like it is converging, then it does converge. So basically, if I have to define it more formally, it's a metric space where the Cauchy sequence converges, then it is known as the complete metric space. Okay. And that take me to the second last thing for today, which is the Banach space. And now these are spaces that you have probably heard about. Banach space you have heard about. What is the Banach space? It's a norm space which is complete. So it's a complete norm space. Okay. And what does complete norm space means? That in this space, in the space of norm, you have a convergence series, and if you have that convergence series, it will converge. Okay, the Cauchy sequence basically. Lastly, we have the Hilbert space that I think many of you heard about. What is the Hilbert space? It's a complete inner product space. Okay. So finally, it is the Hilbert space, and we'll work in this Hilbert space. So I wanted to define this Hilbert space. That was the only objective for today. For that, I told all of this story. Hilbert space is, it's a complete, or it's a inner product space that is complete. Why do we care about Hilbert space? Because if you can show that some function belongs to Hilbert space, then your life becomes easier. Anything that is applicable in the Rn space, the vector space or the Euclidean space, everything holds here. For example, in the Euclidean space, you know that a vector can be represented using basis vectors, E1, E2, E3. So in the Hilbert space, any function can be represented using basis functions, which is f1, f2, f3, or phi1, phi2, phi3, whatever you call it. So once you know that your function is in the Hilbert space, all the properties of Rn space, Rn is a real space, now holds for this space.
So that is not true for the Banach space.
No, it is not true for Banach space. That is only true for Hilbert space. So for example, you know about Gram-Schmidt orthogonalization. You do it for vector, that is also valid for Hilbert space. All the things that you have read in vector calculus will now be valid for Hilbert space. You do not need to prove those, given that you know that a function is in the Hilbert space. That is why Hilbert space is so important. So anything, orthogonalization, all the properties that you are aware of holds in the Hilbert space. So that's why we always work with the assumption, let our function be in the Hilbert space. That is the primary reason we do that. But the most important thing of Hilbert space that we are going to use is that any function f can be represented as summation of Ci psi I. But what is psi now? What is psi? Not just any basis function, orthogonal basis function. Because E1, E2, E3, these are orthogonal vectors. This has to be orthogonal basis function. So if you know these basis functions, you can represent it in terms of orthogonal or orthonormal, that is what we will use, basis. So, I will stop here. I will start with the orthonormal basis next time, but this itself is the foundation of PCE. This is the foundation of PCE that we will talk about next time. So, I will start from here. Any idea how can I find out this C, Ci or Cj? I don't want another answer. Obviously, you can find it out again using regression. Everyone knows that. I'm not asking about that. I just now told you that any property of the vector space holds for Hilbert space. Now, from that point of view. Huh? Of f and psi I or psi j. If I do an inner product of f and psi j, what will you get? That's what it happens, right? Inner product of a vector with a basis function gives you the magnitude of that in that projection, right? That's what you will get. So I'm not doing it today. I'll prove it next time. That will hold, and that will hold because psi I is the orthonormal basis, and because it is the orthonormal basis, it will hold the property of orthonormal basis. Okay. So we'll start from Hilbert space next class lecture. We'll revise Hilbert space and then proceed with polynomial chaos expansion. Okay. But the main thing is that it's good to know about this. It's useful because everything will now be in Hilbert space, and now you will know why can I use all those vector operations on these functions, because these are all in the Hilbert space. Okay. Thank you.